Hi there, everybody. I'm never sure when this actually starts recording or not. Sometimes it's a little glitchy on the computer. Anyway, welcome to another thrilling rendition of chemistry from Professor Staples' basement. Today, we're going to talk about solution concentrations. Many of the reactions that we discuss in a course like this, in fact, many reactions that just take place in general, take place in some sort of aqueous solution. In other words, the substances that we're reacting together are dissolved in water, and that water provides a medium for the substances to then find each other and react. And so we need a way to tell how much of a substance is actually dissolved in water. And not only that, not only for sort of those purposes of aqueous reactions, from an environmental perspective, we need to be able to tell, for instance, how much of a contaminant might be in a water source, or from a medical and pharmaceutical standpoint, we need a way to tell how much of a particular medication or some sort of treatment, how much of that is in an IV bag, something like that. And so we need to spend a little bit of time talking about the concentration of things. How much of our substance is actually dissolved in a solution? Remember back in the very beginning of the course when we talked about classification of matter, and one of our classifications was solutions, homogeneous mixtures. That's really what we're talking about here. We're talking about some sort of solute dissolved in some sort of solvent, and we need a way to quantify exactly how much of that solute is actually dissolved. And so that's what today's discussion is all about, is that sort of quantification and an investigation of different units that might be used for different purposes when it comes to concentration. And so, sort of as mentioned, the amount of solute per volume is known as our concentration. The units of concentration will quite often vary. They might be based on the mass of some of the substances, might be based on number of moles. It depends on sometimes what discipline that you're talking about. Biologists tend to use certain units, chemists tend to use certain units, so forth. Doctors and the pharmaceutical field tend to use other units. But it's always that same basic idea of how much of that solute is dissolved per unit volume of the whole solution. So concentration is always a ratio. And so the bottom is nearly always, and I'm trying to think of if there are any exceptions, and I can't think of any off the top of my head, but nearly always the bottom of your ratio is going to be the volume of the entire solution, or the mass, but it's going to be the amount of the entire solution, not just the solvent. So that's an important thing to keep in mind, and we'll see that in a couple calculation examples. But that is always the amount of the entire solution, not only the solvent. And so some of our concentrations could be mass. Maybe we've got the mass of our solute divided by the mass of our solution, mass to volume, maybe the mass of again, a mass of our solute to the volume of the solution, volume and volume, and so on. Moles we'll work with. We'll see this one a fair bit, especially in this course, and in 114, you'll see molarity, which is the number of moles of solute per volume of solution. And then we'll briefly talk about something called equivalence. And so let's start looking at some of these. And so, a couple examples. And so, mass to volume concentration. Quite often, the concentration of blood solutes is recorded as a mass to volume, very often milligrams or micrograms per deciliter. Great example is cholesterol. For those of you who are looking at health sciences and have started to look at some of these things, or even those of you who have had your own cholesterol levels checked and you're looking at those numbers, you know that one of the so-called magic numbers is 200. We want to be below a level of 200 for our cholesterol. And that 200 is a milligrams per deciliter. And so ideally, we would like our cholesterol levels to be at a level that is 200 milligrams of cholesterol per deciliter of blood. And so there's a concentration unit. How much cholesterol, what's the mass of the cholesterol per unit volume of blood? We'll sometimes even bump that up to a percentage, just change it a little bit. IV solutions are a great example of that. And so very often for IV solutions, we'll take the grams of the solute divided by milliliters of solution. So like there's a mass to volume concentration, and we'll just multiply by 100 to convert to a percent. And a lot of great examples here of some common IV concentrations. If any of you started working in some of your clinicals, those of you going into the health fields, you've probably seen some of these in your work so far, such as a normal saline solution, 0.90% NaCl. And so again, what that means is that per volume of the IV, per volume of that IV bag, 0.90% of that mass is an NaCl. Or 5% dextrose, that would be a D5W solution. Dextrose, 5%. D5NS, combination of the 5% dextrose and 0.9% NaCl. Or something called lactated ringers. I honestly have no idea what that's used for. You don't want me to attend to any of your medical needs, certainly. But some of you may have seen this, or some of you may encounter this, depending on what field you're entering. And again, so that's just a combination of different mass to volume percent concentrations of various solutes, various things that we're trying to deliver to the patient, divided by that volume of the IV. Let's look at an example calculation here. So a certain bottle of tile cleanser contains 135 grams of HCl and 775 grams of water. We want to know the percent by mass of HCl. And so let's just take a look at that calculation here. So we have 135 grams of HCl. So let me go back real quick, and 775 grams of water. And we want to know the percent mass of HCl. So the first thing that we have to remember is that our mass to mass, our ratio there, that is our mass of our solute divided by the mass of the entire solution. And so for the entire solution, we're going to take our 135 grams of HCl, add that to our 775 grams of H2O. And I'm recording this early on a Sunday morning. And so I am going to go ahead and do that math on a calculator. 910 grams of total solution. And so we're going to take our 135 grams of HCl, divide that by our 910 grams of our total solution. And if we're being mindful of our significant digits in our operation up here, we added. And so our rules for addition and subtraction mean that we go to the least accurate decimal point, which would be the 1 spot. So we really should have a decimal point here, which means in our division, we're going to have 3 significant figures. We are going to multiply this by 100 to convert to a percent, and we come up with 14% by mass of the HCl, which is what we see here. So again, that's one of the key things to keep in mind, is that we are talking about the mass of the entire solution, which should go down in the denominator. Another example, rubbing alcohol. Oh, sorry, just a sec. Okay. And so here we have some rubbing alcohol, which is typically sold at 70% by volume. We're given the density. We want to know in this case how many grams of the isopropyl alcohol are actually present in a certain volume, in 355 milliliters. And so in this one, we're told that it's 70% by volume. And so we have to remember that 70% by volume, what that actually means, and so 70% by volume means that for every 100 milliliters of my solution, 70 milliliters of that is my isopropyl alcohol. And so we can use that. What does this suddenly look like? 5 points to you if you said conversion factor. It's exactly what it can be used for. So that's how we're going to convert back and forth between, that should be 70 there, sorry. How we're going to convert back and forth between our volume of actual isopropyl alcohol versus our volume of the entire solution. And so we were told that we started with 355 milliliters of solution in general. That's what's coming in the bottle. We're told that 70% of that by volume is the actual isopropyl alcohol. And so that would get us to milliliters of pure isopropyl alcohol, but we were asked to find the grams. So now we're going to use our density. Here's another conversion factor of 0.785 grams of the isopropyl per milliliter. We do all of that math out, and we would come up with 195 grams of isopropyl alcohol. This would not be something that would be far-fetched to have to do for various calculations. Again, sort of if we don't look at the particulars of this, if we just look at sort of overall what we're being asked here, we have a certain sample of something. So we have some sort of homogeneous mixture, some sort of solution, in which we know the percent by volume concentration of our solute of interest, which is dissolved in there. And we want to know in a particular amount of that, in some particular volume, how much of that actual solute are we getting? How much of the thing that we're really looking for is present in that volume of solution? Could be some very good information, some very useful information, depending on what it is that we're looking for. So, and again, it all sort of comes down to that idea of concentration, of knowing how much of that solute of interest is actually dissolved in our solution. Very key information. For very dilute solutions in which there's not a lot of solute in there, we use parts per million or parts per billion quite often. This is very often used for different environmental for different environmental applications. If we want to know how much of a particular contaminant might be in a solution of water, might be in our groundwater, or in a certain river body, like in the Green River Project, for those of you in CHY 114. And so and for those, we quite often use these parts per million or parts per billion. Fairly easy calculation. So you would go from maybe something like this, which is a percent mass to volume. That's not one that was in our initial examples that we looked at, but that's another fairly common one as well. Percent mass to volume. So mass of the solute of interest over volume of solution. It's another just concentration unit that might be used. And so we could go from there. So normally to find that one, we would then just multiply by 100. But instead, if we take our grams of solute, whatever our compound of interest is, or just species of interest, our grams of solute divided by milliliters of solution times 1,000,000 gets us to our parts per million. Our grams of solute divided by milliliters of solution times 1,000,000,000 gets us to the parts per billion. And so, again, keep in mind what those are. What that's saying is if I have some sort of solution that is, let's say I know that it's just sugar water, nothing in there, it's pure water with a little bit of sugar mixed in. And so that's my entire solution. If I had let's say a 10 ppm solution like that, then what that means is if I take the entire solution, and so water molecules and glucose molecules, that entire solution all together, if it was, I forget what I said, 10 ppm, and so if I have 1,000,000 of those particles, since that's 1,000,000 of a mixture of both, 1,000,000 of a mixture of water and sugar, 10 of those in a 10 ppm solution are going to be sugar molecules. The other 990,990 particles are going to be water. Same thing with the parts per billion. Same exact idea. Let's look at an example of those. And so here, we're given an environmental example where the EPA sets the drinking water standard for the acceptable level of arsenic at 10 parts per billion or less. And so we take a sample of water, 750 milliliters of water, and we're able to actually measure the amount of arsenic in there. And we find that it's 37 micrograms of arsenic. And so ultimately, in some of these cases, we might need to know, does the homeowner need some sort of water treatment system to take care of the arsenic in there so their water is safe to drink? And so we need to take this information, 37 micrograms in 750 milliliters, and we need to convert that over to a ppb. We need to convert that over to parts per billion. So let's look again at our calculation. So ppb equals our grams of solute divided by milliliters of solution times a billion, or times 10 to the ninth. And so we have 37 micrograms of arsenic. And so we need to take that micrograms of arsenic and convert that over to grams, first of all. And so we have 37 micrograms of arsenic. We're going to convert that over to grams. We know that there are 10 to the sixth micrograms per 1 gram. Note, just again with the metric conversions, that you can think of that either way. If you instead thought of this as 10 to the negative 6th grams per 1 microgram, same exact conversion either way, doesn't make a difference. It's just a question of if you're thinking from the terms of the metric prefix or from the terms of the base unit. Same exact conversion either way, though. And so let's just go back and take a look at our calculation then. There we go. And so now we would have our grams of the actual arsenic. And so that's going to be, what do we have there? 37 divided by 10 to the 6th. 3.7 times 10 to the negative 5th grams of arsenic. So we're going to take that 3.7 times 10 to the negative 5th grams. Remember, divide that by our milliliters of solution, which was 750 milliliters, 750.0 to be precise. Actually, we're not going to equal that out yet. We still need to multiply that by our 10 to the ninth to convert that to a ppb. And we come up with 49 parts per billion arsenic. And so at 49 ppb arsenic, that is above our threshold of 10. And so the answer is yes. And that elicits a big sigh, especially those of you maybe who have gone through something like this. Maine groundwater, in particular, with all of our bedrock and our granite, or all the granite in our bedrock. Maine groundwater is famous for having arsenic. We had to go through this. We've got a nice reverse osmosis system in our basement, sitting about 20 feet over that way to my left, to make sure that our drinking water is safe and below the EPA level for arsenic. And so that's how you would run through a calculation like that. One of the more common ones that we're going to use in this class, and certainly in 114, I'll just pull this up a little bit, is what we call a molar concentration. Molar concentration is the amount of moles per our liter of solution. So the calculation would look like this. What we call molarity, abbreviated with a big M, is moles of solute per liters of solution. Let me repeat that because we're going to use this fairly often. Like I said, both in this course and in 114, you'll see this quite a bit. Our molarity is equal to moles of solute divided by liters of solution. You've seen the top part of this chart before when we were going over just different mole conversions. Now here's the bottom, just sort of one more piece in this puzzle of how we deal with amounts of things in a course like this. We can see that once again, for a lot of things that we do in this class, moles is sort of central for us. And so molarity now gives us another way to work with moles. If we have some sort of homogeneous solution, molarity allows us to determine how many moles of our solute are in a certain volume of our solution. So it's another way that we're going to work with converting back and forth with moles. Let's look at an example. So we want to calculate the molarity of an NaCl solution that contains 0.5 moles of NaCl per 2 liters of solution. And so once again, molarity, capital M, that equals our moles divided by our liters. So fairly simple calculation here. We get, what was that, 0.5? This is 0.500 moles over 2.0 liters, which will give us an ultimate concentration of, oh, there it is, 0.25 molar. And so that would be, again, the way we would express that, 0.25 big M. And that big M, when you see it like that, a capital M, you would read that as molar, 0.25 molar solution. Here we have another example, and this is something that would be fairly common. And so now we know in this example, we have a certain mass of calcium nitrate. We have 0.585 grams of calcium nitrate dissolved in 250 milliliters of solution. And we need to know the molarity of that. And so once again, bring yourself back to the actual units of molarity. And so molarity equals our moles over our liters. So the first thing we're going to have to do is convert to moles, because we're given our grams, so we can use our molar mass to convert over to moles. We have 0.585 grams of our calcium nitrate. And so then we're going to use our molar mass. 1 mole of calcium nitrate weighs 164.09 grams. Let's see what that gives us for moles. 0.585 divided by 164.09. You'll note once again, oh, sorry about that. There we go. My very messy calculation. But you'll note that I'm not doing any of my significant digit rounding till the end. For now, I'm still carrying through most of the figures that my calculator gives me. I'll do my sig fig rounding at the very end of the calculation. But now we know that this is dissolved in 250 milliliters of solution. I always forget to switch back over. There we go. 250 milliliters of solution. Might need to pause here for a second to charge my iPad pencil back up. And so we do need to convert that to liters. And so our 250 milliliters of solution is going to be equal to 0.25 liters. And so we're going to then divide this then by our 0.25 liters, divided by 0.25. Gets us to 0.014. Rounded to 2 significant figures because we had 2 in our initial measurement here. All right, you won't notice anything because it's just going to pause the video. Just look like a little bit of a glitch in the matrix. But I'm going to pause the video just to let my iPencil recharge a little bit. We'll be right back. And we're back. And so now we're going to talk about, or look at some examples of, or look at the process of what we have to do in order to prepare certain solutions of a certain concentration. One of the more common things that has to be done in various prep rooms or in various labs in general, people always need solutions of certain volumes of a certain concentration for whatever they might be doing. Think of Dr. Woodruff, works in our biochem lab. He always needs various buffers of certain solutions, and those buffers have to be a certain concentration. And so he has to be able to know, in order to make those solutions, how much of the solvent you actually need in that volume in order to make that solution. And so again, let's sort of keep in mind what we're talking about here. Let me just, yeah, okay, I just wanted to look ahead at some of the other slides coming up. But if we keep in mind what we're really talking about here, let's say just to throw an example out there, if, oops, and I'm not sure where my, oh, I came unplugged here. Hold on. We're back. There we go. Sorry about that. And so let's say just as a complete example, let's say that we need 250 milliliters of a 0.05 molar NaCl solution for whatever we're doing. This is what we need. And so if we think about what we need to know in order to go into the lab and make this solution, quite often chemicals like this exist as solids on our shelves. And in fact, we certainly have, if you go into our stock room, we certainly have a big bottle of sodium chloride to help us make solutions for whatever we might be working on. And so we have some solid NaCl. And so what we need to know is how much of that NaCl, what mass do we actually need? How much of that NaCl do I need to weigh out in order to make my 250 milliliters of solution? And then once we have that, we would use various tools, such as this volumetric flask, in order to actually make that solution. You'll see these when you work with this in lab. We use, in fact, these volumetric flasks here. You can see this little line here. So the only thing that this particular flask exists for, this is a 50 milliliter volumetric flask. This exists to make 50 milliliter solutions. And so in this particular example, whatever they're making here, they've measured out their solid. So they know they need this much solid, add that to the flask. Then you add enough water so you get up to the line. That line is at 50 milliliters. And so then you have a 50 milliliter solution of whatever this is that they're making. Again, keeping in mind that when we talk about volumes with these, we're talking about volumes of the total solution, solute plus solvent, which is why they added the solute here first, then added enough water so that the total volume, solute plus solvent, total volume was at 50 milliliters. So that's important to keep in mind. So here we just sort of see that process playing out. Again, same idea here. In this case, it looks like we're making a potassium permanganate solution, KMnO4. Measured out a little bit of potassium permanganate. We'll add that into our volumetric flask. And sometimes when you're making solutions like this, what you want to do is add a little bit of water in there, not your full amount, but you add a little bit in to then dissolve your solid first. So now we're at a point that our solid is completely dissolved, but we don't have 250 milliliters yet. And so then we add water to get up to that 250 milliliter mark with this particular solution. And so here's an example. In this example, we want to prepare 250 milliliters of a 0.450 molar sodium phosphate solution. And so we have to figure out how we're going to do that. And so again, if we keep in mind what we actually have to know to go into the lab, we have, in order to make this solution, we need to know how much of that sodium phosphate to weigh out, how much of that solid that we actually need to use in order to make our solution. And so what you want to start with here is the volume that you're looking for. In this case, we want 250 milliliters, but keeping in mind that molarity is always in terms of liters. So we're going to convert this over to liters. Then I want to use my molarity. So my target molarity is 0.450 molar. Now, if I stop the calculation right here, if we look at what that would leave us with, stop the calculation here, and that would leave me with moles. I would know how many moles of sodium phosphate that I need to make this 250 milliliter solution. But that doesn't do me much good at this point. I don't have a balance. I don't have a scale that's going to tell me the number of moles, that's going to allow me to measure the number of moles. So I need our final bit of information. I'm going to use my molar mass of 163.94. Remember, that's grams per mole. And if I do out that entire calculation, so my 250 divided by 1,000 times 0.45 times 163.94, I get 18.4 grams of my sodium phosphate. And so remember, what that tells us is that I need to take 18.4 grams of sodium phosphate, and I'm going to take that, and then I'm going to add enough water until I get a total volume of 250 milliliters. And so in that, then, that means that when I'm done, I'm going to have a 250 milliliter solution that will be at 0.450 molar. It will be at my desired concentration. This is one of the more common calculations that is done, like I said, in various chem prep labs. When I'm working in the back prep room, helping get things ready for 114, I'm doing this calculation all the time. You might go back in there at some point if I'm really doing a lot of work, prepping a lot of the solutions. You'll see post-its with this exact calculation. You'll see little post-its that look like this all over the place, because I need to scratch out and figure out, again, how much of the mass do I actually physically need in order to make my solution. And so that's the process that we would use if whatever solution we're making, if we have that product sitting as a solid on our shelf, this is what we would do. Sometimes whatever we're working with does exist as a liquid, and we have it stored as a liquid, rather, or we have it stored as, not necessarily as a liquid, sorry, but we have it stored maybe as an aqueous solution. Acids would be a great example of this. We have concentrated acids back in the back stock room. And so those are, depending on the acid, usually ranging anywhere from about 12 to 18 molar. Typical concentrations that we would use in the lab, though, are more like 0.1 or 0.025 molar, something like that. And so again, though, the information that we would need, let's say that I need to make 2 liters of 0.1 molar HCl. I need to know how much volume of the 12 molar HCl do I need to take that and then dilute that up to the 2 liters in order to have my target molarity. And so to do that, we use what we call the dilution equation. M1V1 equals M2V2, in which typically, not gonna worry about that. Okay. And so our M1V1 equals M2V2. M1V1 equals M2V2. Usually the way that these equations will be set up, or sort of the way that they'll work, is that M1 will typically be the molarity of whatever your stock solution is, whatever solution that you're using to make your desired solution. V1 will be how much volume of that solution do you need? Quite often, this will end up being what we're solving for. M2 will be our target molarity, and V2 will be equal to our target volume. So I was just looking to see if there's anything I really want to talk about here. About the only thing to mention here, C1V1 equals C2V2. Same exact formula, same exact calculation. The difference is the C as opposed to M. Remember that molarity is just a concentration unit. This dilution equation can be used with any concentration units. You could do this with ppb, ppm, percent mass volume, doesn't matter. You could use this equation with any of our solution concentrations. So you might see C1V1 equals C2V2 in various sources that you use. I may use them interchangeably, but remember it's the same basic thing. Let's look at an example. And so pretty close to the one that I was speaking about earlier. So in this one, I have 12 molar HCl. That's what I've got sitting on my shelf is a 12 molar aqueous solution of hydrochloric acid. I need to prepare 1,000 milliliters of 0.1 molar. So again, let's just think about what we're doing here. If I'm physically in the lab doing this, I need to know how much of that 12 molar HCl do I use, and then how much of that 12 molar HCl do I pour into a 1,000 milliliter volumetric flask? How much of that do I put into my flask so that I can then dilute that amount up to 1,000 milliliters, and I would have my 0.1 molar HCl solution. And so we're going to take our friend M1V1 equals M2V2, and we know that M1 is our 12 molar. That's our stock solution of the hydrochloric acid. V1 is how much I'm actually going to need. I don't remember my targets here. What is it? 1,000 milliliters of 0.1 molar. So reverse those, didn't I? So my M1, I'm looking for 0.1 molar. V1, I've got 1,000 milliliters. Keep in mind, you might have caught this, that yes, molarity works with liters, but in our dilution equation, your volume can be in any units as long as you're consistent. And so the fact that I'm using milliliters for my V2 just tells me that when I solve for V1, that will also be in milliliters. And so your units for any part of this dilution equation, you can have any units of concentration, you can have any units of volume. Those units are just going to be the same on both sides of the equation, but it doesn't matter ultimately what units you use. They just have to stay consistent. And so now we're simply going to solve for our V1. So we get 0.100 molar times 1,000 milliliters divided by our 12 molar. Look at our units, by the way, and what happens with those. Molar will cancel out, leaving us with milliliters. So that's good because we know we're looking for a target volume. And so we plug this into our handy dandy calculator. We get 0.1 times, maybe we do if our calculators turn on, and they don't. Luckily, I think I've already done it. There it is. Gets us to 8.3 milliliters. And so if I'm in the lab making this, that tells me that I need to take 8.3 milliliters of my 12 molar solution, dilute that to a total of 1,000 milliliters, and I'll have a 0.1 molar HCl solution. One of the last things to talk about today is to note that is to discuss our concentration of actual ions. So remember that when an ionic substance dissolves, the ions actually break apart from each other into the solution. This is something we'll be getting into a little bit more detail on within a week or so. But for now, just know that this is what happens. In an NaCl, when I dissolve solid NaCl, the sodium ion separates from the chloride ion. And so I now have those two distinct ions floating around in my solution. And so the other thing that means is that if I have, for instance, an NaCl, for every one, or an NaCl solution, for every one unit, so to speak, of NaCl, I actually have two ions in there. Right? I've got one sodium ion and one chloride ion. If I have an MgCl2 solution and I dissolve that, that means that for every one unit of MgCl2, I'm going to have one magnesium ion and I'm going to have two chloride ions. A sodium phosphate solution would dissolve into 3 sodium ions and 1 phosphate ion. And so there might be times that we want to know the concentration of a particular ion in a solution. Now, for those NaCl solutions, there we go. So I've got the examples right here. Let's say I have a 0.25 molar NaCl solution. Since this is just a 1-in-1, I have one Na ion for every one NaCl. I have one chloride for every one NaCl. That means that in a 0.25 molar NaCl solution, I've got 0.25 molar sodium, and I've got 0.25 molar chloride. In an MgCl2 solution, let's say I have a 0.015 molar MgCl2 solution. It's 1-to-1 for our magnesium, so I've also got a 0.015 magnesium solution of, sorry, I've got a concentration of 0.015 molar magnesium ions, but I've got 2 chloride ions in there for every 1 mole of magnesium chloride. And so that means that my concentration of chloride ions is actually 0.03 molar. Likewise, for our sodium phosphate, a 0.7 molar sodium phosphate solution, for every 1 mole of sodium phosphate, we have 3 moles of sodium ions. And so in a 0.7 molar sodium phosphate solution, I have a concentration of sodium ions of 2.1 molar and 0.7 molar phosphate in them. Oh, I thought I went to another slide, but I don't. This is what's known as equivalence, was the last concentration unit to talk about. And so you may have times when, and this seems to come up, if I remember right, mainly in some medical applications and some certain IVs. You might be looking at what the equivalent volume is, and that would be a situation like this, that maybe you're using a sodium phosphate solution, but that's got an equivalent concentration of 3 times that for our sodium ions. So that would be something to keep in mind when you're maybe delivering sodium to a patient, is that you might use perhaps, and I don't know if you really would. This is just me sort of giving examples. Again, you don't want me involved in your medical care. But let's say you're using sodium phosphate to deliver sodium to a patient. So you would have to remember that whatever the concentration is of the sodium phosphate, the equivalent concentration of sodium is going to be 3 times that, because you get 3 sodium ions for every 1 unit of sodium phosphate. And so that is it for our discussion of, sorry. As I'm recording this, my wife is out with the kid right now, and there's a nice picture of him watching sailboats as they have breakfast. So there you go. There's a little treat for you. So that was our discussion of concentration. It's something that we will be using a fair bit in this course. You'll be using it some in lab, making your own solutions and doing some various things in there. And that is about it for today. And so thanks for watching, and you stay classy, USM. Have a great day.